Take it away.
Hi there, data scamps and data champs. This is Richie. It is a sunny day in New York. You can tell because my glasses, the photochromic lenses have kicked in. It looks like I'm wearing sunglasses, which makes me feel very, very cool. All right. Yeah, please do tell us in the chat where you are joining from. And we're going to kick off pretty much straight away, actually, because we are running a little bit behind. So today's session was actually inspired by a debate. So we had an argument in the office about, can you do statistical modeling in SQL? And after a bit of research, it turns out the answer is kind of yes. So with DuckDB SQL that we're using today and a few other variants of SQL, there are functions to run simple linear regressions, and it's also possible to do sort of simple optimization. So while I wouldn't necessarily want to try and create a large language model in SQL, you can do some statistical modeling. And so that's what we're going to learn how to do today. And we've got a very nice example around optimizing product prices in order to maximize revenue. So there's going to be a bit of technical SQL work, a bit of mathematics, and a little bit of product economics. Our guest is Joseph Wapples. He's a data science content editor here at DataCamp. So that means Joseph is the editor for our data science and statistics tutorials. And Joseph has a technical background, previously worked in healthcare data science at TrueLeave, Simple Health, and Columbia Care. So he's written so much on data science in the last few months. I'm very excited for his first code along. Please take it away, Joseph.
Awesome. Thank you, Richie, for that introduction. Yeah, I am a data science editor here at DataCamp, but I've never done a code along, so I'm very excited to do that. And as you said, we're going to be doing SQL. We're figuring out an optimization problem in SQL that I think is going to have a lot of uses in a lot of different places. And so I am very excited for it. I can pull up the notebook right now. Can you see my notebook? Yes. Okay, so pricing optimization in SQL code along. So the business problem here is, well, businesses care a lot about the prices of their products. Businesses always, they sell different things, and they want to make sure that they sell whatever they're selling, widgets, bicycles, trees, horses, whatever it is, for the right price. If they price the product too low, they're going to lose revenue. And if they because even though they sell a lot, they don't generate very much money. If they price the product too high, no one's going to buy it. And so you're not going to generate any revenue. So the question is, how do you find the price of a product that maximizes your overall revenue? And business leaders everywhere, regardless of industry, they're all going to care about this problem. But a lot of people don't know if they have like an analytical tool to figure out the exact way to solve that problem. So we're going to do that right here. So the goal of this code along, we're going to take a data set, a simple data set with two different variables, price and quantity sold, and we're going to use that to find the price that maximizes revenue. And so specifically, the specific questions we're going to answer is, what is the price of the product that maximizes revenue, as I said, but also on the other side of that, what revenue can you expect after you optimized for price? This code along will have three parts. The first part is performing a linear regression in SQL. And the business case here is we're going to find a function that describes quantity sold as a function of price. And we're going to figure out the linear model coefficients in SQL. And by coefficients, I mean the slope and the intercept, the two ways in which you describe the line. And the SQL learning here is we're going to have some practice with common table expressions. In part two, we're going to actually understand more about the relationship between price, quantity sold, and revenue. So we're going to introduce a third term here, a new term, revenue. And we're going to define revenue in a particular way. And we're going to take our linear model and we're actually going to make it a polynomial regression, specifically a quadratic regression, because we're going to describe price by a squared term. And in this section, we're going to use SQL subqueries. And then in the final part, we're going to explore the intersection between math and coding. And you'll understand, we'll have some discussion around calculus and algebra and derivatives. And so that's going to be exciting stuff. So you're going to really see how we can actually make use of an optimization problem in SQL. All right, so as a quick SQL refresher, I put in here the complete list of different functions we're going to be using in this tutorial, and I grouped them by type. So we have aggregate functions. This will take like a data set with 200 rows and create one row, which is an aggregate of whatever you're looking at: count, sum, average, standard deviation, correlation. DuckDB is also very cool. It has specialized linear regression functions. So after we do it the longer way, let's say, we'll have access to a shortcut, which is going to be really useful as our queries start to get a bit longer. With, as are keywords that you probably recognize if you've written common table expressions. And then we also will use mathematical transform functions here, specifically ln for the natural logarithm and exp for how to exponentiate. So to back transform our model after we're done with it. Our data set. So this data set is something that I created myself. It just has two features: price and quantity sold. And it's only 200 variables long. And each row corresponds to one day. So imagine, for example, that a company's decided to sell products for $10,000. And then they sold 50 of those products that day. So they generated 500,000 in revenue for that day. So that's how that works. Where each day is an observation, and when it's 200 rows long, you kept track of your data for, a school year, and then we'll now want to do some analysis on it and figure out how to optimize pricing. All right, now I think we're ready to get started. So the first thing, part 0, I didn't mention part 0, but there's always a part 0. Part 0 here is doing a little exploratory data analysis and warming up and getting ready for SQL. So you'll see how this works. There's a code block here, which is the code block here. It has our right above the code block, we have instructions. And so you can read these instructions and figure out what we're trying to do. And I'm going to be doing this coding here along with you all. So you can see how I'm thinking through this problem. All right, so the first one, we select price and quantity sold from our data set. Select, you can also do star from, but let's do price, quantity sold from demand curve data dot CSV. And then I'll hit the run button. And we can see here two columns, price and quantity sold. And it comes with an index, and the index is really referring to the days. So on day 1, let's say you sold your products for a cost of 10,000, and you sold 56 of them. The range here is 10,000 to 40,000. So it's not labeled. You can imagine we sold, designer watches or motorcycles or whatever. And that's the beauty of this, is because this kind of analysis you can use anywhere, as you'll see. All right, so the next step of exploratory data analysis is data visualization. And Data Lab has great ways to do visuals. They're beautiful visuals, and they sit right alongside the code. Because data visualization is important here, because if you look at these two columns, you really can't get a read on what the relationship looks like. That's why we visualize it. So here I will visualize it. I'll do the same code. Select price and quantity sold from our demand curve data. And this time when I hit run, I'll create a scatter plot. It was already toggled over to the chart, so it created a scatter plot automatically here. And now we can see the relationship in this data set of the price of the products to how much you sell. And there's something that is obvious in this relationship, which is, as you increase the price of the products, the quantity sold decreases. And so that's obvious, because everyone likes a deal. But you can also see something maybe that's a little less obvious, which is that there's a little bit of curvature in this line. And that makes intuitive sense also, because the customers over on the far right end are not going to be so price sensitive. So you increase the price by a lot here, but they still buy a similar amount. But on the low end, you have certain customers who only buy a lot, these, for example, when the price is very low. So these customers are good at finding a deal. So as a result, we have a little bit of curvature in this model. And that's something that we'll handle a little bit later on in this code along, but I'm calling it out now because these are the two obvious things that I see. Okay, so how do you perform linear regression in SQL? This is not a linear regression, to be clear. This is a scatter plot, but it implies, when you see a scatter plot, it often implies a linear regression in my head because you want to put a line through it. So performing a linear regression in SQL. The first step is to review formulas for linear regression. And there are a lot of different formulas. You could describe linear regression in terms of variance and covariance. I have some neat closed form equations that I think are very useful. But we'll review these, and then we'll also use SQL aggregate functions in order to create the parts that we're going to be plugging into these formulas. Okay, so the linear regression equations. A here, A refers to slope, and I refers to intercept. And if you look closely at these equations, you'll see that it's convenient to solve for the slope first because A will appear in the equation for the intercept. And you can describe the slope of linear regression as the Pearson correlation R multiplied by the quotient of the standard deviation of Y over the standard deviation of X. Now, this formula I really like because you're really saying that it's the correlation between the two variables, A and B, X and Y, put back onto the scale of the original data, which is why you're multiplying by the quotient of the standard deviation of Y over X. And then if you look at the formula for the intercept, you have Y bar, the bar above Y you pronounce as Y bar, and the bar above X you pronounce as X bar. So you're putting that regression line, you're setting the intercept so that the regression line goes through the center of mass of the data points, which is why linear regression has that sort of balancing property. So these two equations I like. And just to be clear, I'm talking about simple linear regression. And by simple, I mean regression with one dependent and one independent variable. So you cannot do multiple linear regression in SQL, just to be clear on that. If I had a data set with 3 columns, I wouldn't be able to create a regression on one variable based on the other 2, because you need linear, in that case, you would need linear algebra to solve for the coefficients. But simple linear regression, you can do fine. Okay, so now we're going to find the coefficients for simple linear regression, but the first thing I wanted to try here in this code along is to do a refresher on common table expressions. So if you're not familiar with common table expressions, I'll start from the beginning. Here we have our instructions. We just want to take our original query where we select star from, or we select price and quantity sold from our data set, and then we're going to refactor it into a common table expression. So I'll show you exactly how to do that. We select price and quantity sold from demand curve data dot CSV. And I'll hit run. So this is our data frame you'll recognize. And the next thing, for me, when I write a CTE, I always just kind of mindlessly say with X as, and then I open a quotation. And I put the quotation at the bottom. Not quotation, parentheses. I say with X as parenthesis. And I put the parenthesis at the bottom, and I hit select star from. And then the data set I choose is the X or whatever variable, but I say X. And then I hit run, and it's the same. So I've added all this extra stuff, but it's the same. As a next step, you can name your CTE, for example, regression data. And whatever you put up here, you'll put down lower in the from clause. And then the beauty of the CTE is I can now alias these things. Select price, select quantity sold. I can say price as P and quantity sold as Q. And now what I'm doing is I'm selecting P and I'm selecting Q. And you see P and Q will show up in the columns of the data frame. So this will be really useful as we're starting to add things together and we want to keep our code clean. So there is a common table expression. So how are we going to do linear regression in SQL using common table expressions? Well, as we said, we can express the slope and the intercept of linear regression in terms of the correlation, the standard deviation, and the mean of both x and y. So let's do that. We'll take it from the top. Okay. I'll give you a minute to think through this, but what we're going to do essentially is we're going to create each of our variables. We want a variable for mean. We want for mean of y and mean of x. We also want the standard deviation of y and the standard deviation of x. We also want to get the correlation between price and quantity sold. We can name each of these variables specific things. And then in the second section of the CTE, we'll make it look like the equations for the slope and intercept that I showed you above. So let's do that. We have select star, yikes, okay, select star from demand curve data .csv. But the star is something I'm going to replace because I'm using aggregate functions. This is going to return the 200 observations I have in the data set, but I'm doing aggregate functions now. So let's do let's start with standard deviation. Standard deviation of price as SD price. And when I hit run on this, you're going to see only one row instead of 200. So let's come up with a standard deviation of quantity sold as quantity sold and the average of price as mean of price. SQL always says average, but then I always make the variables say mean just so I don't think about the median. That's just what I do. Price quantity sold as the mean of quantity sold. And now for the final one, I use CORR for correlation. And here I could do either or. I could do price first and then quantity sold, or I could do quantity sold and then price. It doesn't matter on the order. And I'll save that as correlation. Okay, so here are different parts that I will need for the formula. Let's practice with our CTE again with x as, and then select star from x, and I'll hit run. So that is the same thing. Let's name x something more interesting like regression data. Oh, sorry, pasted that in the wrong place. Select star from regression data. And now what I really want to do is come up with something for the slope as the slope and as the intercept. So what is that something I'm going to come up with? So the slope is the correlation multiplied by the quotient of the standard deviation of quantity sold divided by the standard deviation of price. And the intercept is the mean of quantity sold minus the slope times the mean of x. Now slope doesn't exist so far. I just declared it. Sorry, that was a placeholder. I'm going to copy in this formula here and put that there. No point in doing another CT, I don't think. Oh my gosh. Let's see. Let's try that again. Copy and paste it wrong. Okay, correlation, select. Let's see. Select, so I'm going too fast here. Let's try this. Let's make sure I do this right. So select.
I think you've just got the wrong alias in the first select query. So standard deviation quantity sold as quantity sold, which I think should be SD quantity sold.
Oh my gosh.
Line four. Line 4.
Line 4. SD as quantity sold. Thank you. Yep. So that's why you do not copy and paste, Richie. Thank you. Thank you. SD quantity sold. Okay, so I'll build these up again. It's good practice, right, Richie?
Yeah, typing things wrong is part of the job.
Well, I'm doing a lot of that here. I forgot a comma too. Okay, there we go. Okay, so let's do the slope as slope. Let's figure out the slope. Dun, dun, dun. Okay, so the slope we know is the correlation multiplied by the quotient of the standard deviation of quantity sold divided by the standard deviation of price. There we go. I'll run these one at a time. And the intercept is the mean of quantity sold minus the slope times the mean of price. Voila. And I did not give that an alias, but let's call that intercept. Okay, so here I have found the coefficients for the simple linear regression line that describes quantity sold as a function of price. So when, this intercept is not something that you can interpret, but when the price is 0, you sell 70 of them. Okay, so now on to DuckDB. DuckDB has some very nice functions that let you avoid common table expressions in this case if you don't want to use them. So regression intercept. And this, I have to think about the order. You have to put the Y first here. So regression intercept, quantity sold as a function of price. Call that the intercept from demand curve data dot CSV. And let's do the same. This time I will not copy and paste. Quantity sold and price as slope. There we go. So these are the same numbers. And I think DuckDB is probably just using this formula, or else it's describing the slope and the intercept in terms of variance and covariance, but it's doing something similar. And we are able to get the slope and the intercept without even doing a CTE. So this is the regression intercept, regression slope functions, and they are extremely useful. Okay, so on to part 2, understanding price, quantity sold, and revenue. So in the first part we found the intercepts, the intercept and the slope. We found the coefficients of our model. Now let's think about a new term, revenue. So in this section, we're going to understand that whole relationship, and we're going to look at a quadratic regression technique, which is going to be very fun. So let's take a look at our scatter plot again. So select price, quantity sold from demand curve data dot CSV. Here is our scatter plot. Looks familiar to us. Now, we already said that quantity sold is a linear function of price with an intercept and a slope, which we just discovered. We can also define revenue as price times quantity. So if you sell, for example, 100 bicycles at $100 each, and you made $10,000. So that's in revenue. So that's price times quantity. However, we now have a linear function for quantity sold in terms of price. So if we want to turn this into a modeling exercise, what we could do is we could replace quantity sold for our linear function for price. Now we can describe revenue as equal to price multiplied by beta 0 plus beta 1 times price. And just as you would distribute terms, you have x times 1 minus x, and that would equal x minus x squared. You can distribute terms here and end up with a definition of revenue as beta 0 times price plus beta 1 times price squared. So quantity sold has sort of disappeared here. And we know, excuse me. So we know that, for example, on a scatter plot, we have an X and a Y variable. So it's really convenient, as you will see, to get rid of one of the variables because we give ourselves a new graphing option. And I also just put the derivative here. So the derivative of revenue with respect to price, we're getting rid of price. And then we take the exponent and we put it in front. So that's something I'm putting down. That will be useful maybe if you explore this notebook, as you will see. Now, let's take a minute to talk about linear model transformations, okay? So I mentioned at the top of this notebook the ln function, which uses e, but there's also the log function, which has a base 10 logarithm, and these are different. And this is an important difference for us in particular because we're going to use a log transform, and then we're going to do a back transform using the exp function. And so if we did a log transform using log, but then we did a back transform doing e, we're really going to jumble our numbers. So we don't want to do that. So you can test which is which. You can say ln is 100. Select ln 100. We get a number 4.60517, and it will go on. But if you were to do log of 100, you get 2 as a result, base 10 logarithm. So that's something you could test for yourself. And if you're going to be doing some modeling, you want to make sure you have that straight. Okay, so let's continue. Select price, quantity sold from demand curve data. So here is select price, quantity sold from demand curve data. We can create a scatter chart, right? Oh, shoot. Here, actually, what I actually want to do is move on to creating a log model. So let me move this, for example. Select price, ln of quantity sold from demand curve data. Right, so we can do log transforms on our quantity sold here. So if we were, for example, going to, well, let's see, let's create a chart actually. Let's actually create a chart for real. Price times add a series, log quantity sold. There we go. So here what I did is I selected price and the log of quantity sold and created a scatter plot. And this looks much more linear as a linear model. There's no curvature anymore. There's a little bit of unequal variance here on the right end, but that won't matter for this modeling exercise because what we're doing is averaging. And when we do the averaging, we're creating a model based on the average, and this doesn't matter. Heteroscedasticity would matter, for example, if you're thinking about something like confidence intervals. But it's interesting that that got induced with a log transform, which can happen. Okay, so here we have our equation for quantity sold. It's actually log quantity sold now times the linear function. Log quantity sold is described by our linear model. And so revenue is price times the log quantity sold. And so when we consider this logarithm, our new definition of revenue is revenue equals price times e raised to the expression of our linear model. And then this doesn't distribute quite as easily as the algebraic terms above when you say revenue equals price, but you can simplify it a bit. And so now going forward, we're going to be working with a log transform in our model because by doing the log transform, we ended up with a little bit of a better linear model. Okay, so now how do we graph this? On the x-axis, we want price, and on the y-axis, we want our revenue function. And our revenue function now is this, price times e raised to this expression. So let's do that. the first thing here is we're going to select price, our X variable, from demand curve data. And the thing that we want on the y-axis is e raised to our expression. So exp is the way to do that. So we do exp. And now in order to get exp raised to beta 0 plus beta 1, so we need these coefficients from our linear model, which we need to derive from our own query. So we start a subquery always with the open parenthesis, and then I can select. And here what I want to select is the intercept first, beta 0 plus. And here I'm doing the log of quantity sold, ln price. And I will select it from demand curve data. So when you do a subquery, you are going to need to like specify your table again. But it's not e raised to just the intercept, it's e raised to the intercept plus the slope. So I'm going to create another subquery here, select regression slope. And now you really appreciate these DuckDB functions, because imagine having to kind of do this, it would be nested within another CTE probably. ln times quantities, natural logarithm of quantity sold, price, from our table again. Yikes, okay. So again, typing too fast, from oh wait, here. Let's try that again. Okay. Okay, so I have exp. There we go. There we go. Okay. So now what I'm adding simply is, instead of the intercept, I'm going to find the slope this time. Whoa, what am I doing wrong? Okay. I have the intercept. And now I add it to another subquery. So it's very easy to get within the E2 subqueries. It's very easy to get tripped up with the parentheses. But I will solve this issue. I think I probably just misspelled something. ln of quantity sold price from demand curve data dot CSV. There we go. Okay. So add that, but it's beta 0 plus beta 1 times price. So add price, or multiply by price. But the whole expression is actually price times e raised to price. Price times e raised to the expression. Ta-da. Okay, and this is a terrible column name, so always do some aliasing. We'll call this one revenue function. Thank you for bearing with me. Okay. So now when we graph it, it should take a different shape. It should take a quadratic shape, so a parabola. And there it is. Okay, so great. So now we're defining revenue only in terms of price. And this is really convenient because if you looked well, first of all, what's interesting is that even though you're doing logarithms, you're back transforming. So all of this is back on the scale of the original data. Now, what's really interesting to me is when you go back up here and you see this original graph that describes quantity sold as a function of price, it's like you might guess what's the price that maximizes revenue. Well, if you had 10,000 as the price, you might sell 60, so that's 600,000. And if you have the price at 40,000, you only sell, 10, so that's 400,000. But if the price were 20,000, maybe you'd sell 40, and that's 80,000. 80,000 is more than, 600,000, which is more than 400,000. But like, you're guessing, it could be anywhere in this range. And there's also a lot of noise. You didn't do any averaging. You didn't create a model. So is it a one-off day? Are you looking in the right spot? How much is it going to change? It's hard to see. But here you've taken that out. You can see a parabola, and you can start to see exactly where the price is that would maximize overall revenue. It's somewhere in this range. That said, this range is still kind of a big range, so we can use some math here to like get it more exact. Okay. Now you might be wondering about this picture. So this is from Ferris Bueller's Day Off. This was the boring teacher who was talking about economics. He had a Laffer curve in the background. It's a very funny scene. So the Laffer curve, if you studied economics, this is very similar to the Laffer curve, which is about tax revenue. The idea is that if you had a low tax rate, you generate low tax revenue. And if you had a high tax rate, you might also generate low tax revenue because you've like disincentivized taxable activities. So it's a little bit of controversial, but it's the same general concept. It's about optimizing tax revenues. But here we did it in pricing. Okay, so the next step is to actually figure out in math, like, what is the derivative of the revenue function? If you're not familiar with derivatives, derivatives are something that I talked about in financial markets, for example. Like if a car is going a certain miles per hour, that's its speed, and how fast it changes its speed is the acceleration. And how fast it changes the acceleration is torque. So acceleration is like a first derivative of speed. It's a change in the rate of something. So that's what derivatives are. Now, okay. So how are we going to do this, right? So I'll go through this kind of fast, but you can see I left these as little buttons that you can pull down, but I'm going to show you how to think about it a bit. So there's something called the product rule from calculus. If you have the function of x, which you call f of x, is going to be equal to, let's say, if it is equal to u of x times v of x, then you find the derivative by finding the derivative of the first part, u of x, multiplied by the second part. And then you take the first part and you multiply it by the derivative of the second part. So our revenue function, right, is price times e raised to that expression. The derivative of price is price. It's the derivative of price is 1. The derivative of price with respect to price is 1, because it's like, how fast do you change price as you change price? It's a 1-to-1 relationship. You can put 1 here, and then I'm just putting the second part, and then I put the first part, which is price, and then the derivative of e to that expression. If you have like 2x squared, you take that exponent and you multiply it by the number in front to get 4x. But this is an expression, so you can't quite do that. You have to think through the parts. So beta 0, we know beta 0 is 70 or so. How much does 70 change as price changes? It doesn't change at all, so that's a 0. Price we handled, that's just 1. But beta 1, that's like the scaling factor. You pull that out into the front. And then as the rule goes, you leave the exponent all the same because it's an expression. Now, the next thing you do is you can factor this. So this is a rule from algebra. A plus b times a is equal to a times 1 plus b. If a were 5 and b were 3, it would be 20. It would be 20 on each side. So you can like test that, and you can see that this is true. Now, in our case, our expression here, this is an a part, e raised to the expression that shows up twice. And then there's a b in the middle, which is price times b1. So here we can just do some factoring. And now what's kind of interesting is you want to set the derivative to 0, because that's where this slope stops going up and it starts coming down. So there's a moment there where the derivative is at 0, and that's the top. So you have e raised to the expression times 1 plus price times b1 for 0. Well, you could this is an exponent, so it can never be 0. If it's positive, if price is high, if price is a positive number, that'll be big. If the exponent evaluates to 0, it's 1. If it's negative, it becomes a tiny fraction, but it's never 0. So we're only working with this part. And then I just move the terms around. Right? I put 1 on the right side, and I divide by beta 1. So I get a definition of price as being negative 1 over beta 1. And then finally, to find the revenue maximum. And you can explore this later. You can explore this later. You have to work through it a bit. You can change the definition of price because now you have a definition of price. You always go back to your old equations as being negative 1 over beta 1. And beta 1 here we define as the slope. And what's interesting is it's e raised to the intercept plus the slope times a new definition of the slope. You know what I mean? This slope times negative 1 over the slope will become negative 1. So anyway, this is kind of the intersection of math a bit in SQL. So now we can incorporate our work into SQL here. So let's do this. So let's first of all select the slope, regression intercept, quantities. Well, let's stick with the logarithms, quantity sold and price. Select log of quantity sold and price as intercept from demand curve data. Okay, here's our intercept. And then I'll do it again for the slope. Well, this has to be, okay, so the intercept from demand and slope, regression intercept. Hang on, let's see, select star from, okay, regression intercept, quantity sold and price as intercept, okay. Okay, sorry to do it twice. I just didn't recognize the numbers, but I realized it was only because I was working with a natural logarithm system. So I wouldn't have recognized the numbers. Okay, so let's do our CTE again. Back to the CTEs with X as select star from X, remember. Let's give these X a better name, regression data. But I'm not interested in star. I'm interested in optimal price. Something as optimal price. And I'm also interested in something as max revenue. Now the optimal price here, we just figured out is -1 divided by the slope. And when you have like a little expression like this, you always have to make sure you put the parentheses around it. This wouldn't work. So make sure you do that. And max revenue is -1 divided by the slope multiplied by exp to the intercept -1. Let's see. Okay, cool. So the optimal price is $20,100. And the associated maximum revenue for that optimal price is going to be $733,000. $733,100. So let's go back up to our curve and see where it's $20,100, and that seems to check right there at the top. That is the best price you can come up with for your products to maximize overall revenue in the long run. as a predictive modeling exercise instead of as like a guessing game. So speaking of guessing game, why can't you, for example, just look at your data set and say, okay, let's find the price, let's find the quantity sold, multiply price by quantity sold as revenue, then just order by revenue, descending, and then just choose the top one, limit one. Why can't you hypothetically just do this? Well, you could, but it's noise in the data set. It's not a model at this point. You're just finding the one off day that was the best. And it could have been an unusual day. And in this case, it's saying that the price should be 24,000, not 20,100. It's a big difference. It's a difference of like 15%. It's actually more than that. It's really, I said 3,000, it's really 4,000. So it's a bigger difference than that. It's over, let's say 17%. That's a big difference. 17% really in terms of pricing. It's $3,000 on an object. Okay, so that's the predictive modeling exercise. I wanted to just kind of talk a little bit about the ideas in here. So this is a standard relationship between quantity and price sold. It's a law of demand, but there's certain things, it's not always true. There are certain cases in history, for example, where bread prices went up and people bought more bread because like they didn't have any extra money to buy anything else except bread. So they actually bought more of the thing that became more expensive. So that can happen. And then there's something called Veblen goods. These are luxury goods. So if you have certain customers who are not price sensitive, when like the price increases, they buy more of it because it signals exclusivity and higher status and all that. So, there's definitely, when you're doing pricing strategy, there are analytical tools you can use, but you also, you would also want to consider psychology too. And then I also had like a final note, and I think this was out of scope. You can't do everything in one code along, but you could consider profit instead of revenue. You could like keep going. And you could do that because you could define profit as revenue minus cost, and you could create some definitions around costs as being the cost, as being like fixed and variable costs, specific, so which you could call unit cost. And if you took unit cost as an expression like 1 minus P or price or 1 minus C, then you could get an upside down parabola again. And this time it would be left adjusted because profit is always going to be less than revenue. So this is the code along. I hope you enjoyed it. What I love about this technique is it really feels like you can do a lot with just a little bit. You take a data set with only 2 features, price and quantity sold, and all of a sudden you're talking about optimizations on revenue. And so I think that's very exciting, and I think it's a great opportunity to like stand out as a data analyst or a data scientist. And if a lot of analysts, a lot of different companies will have access to this data set kind of as part of a dashboard. And also I would want to say that like if you're interviewing, I think this is a really good kind of project that you can showcase because it demonstrates your understanding of SQL, and it would demonstrate your understanding of algebra and calculus and statistics, and also your understanding of like you demonstrate that you have business sense too with this. And so yeah, you should subscribe to Data Camp and get a data lab notebook going so you can really play with this kind of stuff. And we have lots of great courses on Data Camp. Linear regression courses, and also courses in data analyst skill tracks for SQL data analyst. Would be 2 that I recommend a lot in particular.
All right, super. Thank you so much, Joseph. That was great stuff. And I definitely agree that if you're looking for projects for your own portfolio, if you're trying to get a job or trying to get promoted, then regression SQL is not something that a lot of people know about yet. 'Cause the regression features were only kind of added to SQL like in the last few years, so it's something that's a little bit new. It's going to help your project stand out, especially if you bring in like a business use case like we did today. We've got time for just a couple of questions from the audience. So this one, so it's related to the idea of trying to get a job using SQL. So there was a link in the chat about some example interview questions for if you've got to like a SQL coding test or whatever in your job interview. Keeping up with Amy asks about like what are some sort of real complex use cases of SQL. And I've definitely got opinions on like what some of the hardest things you need to learn about SQL are. Joseph, do you want to talk through like what are the sort of challenging parts of SQL that you tend to see in real queries?
Oh yeah, well, you saw me trip up a bit there, right? When I was doing I had the E raised to the subqueries. So sometimes the way in which it compiles and the way in which you write it from inside out, that can feel a little unusual. If you're using a programming language like Python or R, you're always like saving intermediate variables and tables. That's a little harder in SQL. It wants to compile in one. So you do have to kind of think about it just a little bit differently in that respect. And that's the thing that I find personally most challenging in SQL. But that being said, SQL, when you get the hang of it, it's sort of easy to kind of debug if you can highlight certain sections and run it by itself. You can identify an issue pretty easily at the same time.
Absolutely. From my point of view, I think there's four tricky things with SQL that we see like a lot of our learners stumble over. So the first one is joins. Like that's the first hard thing you get to in SQL. Everyone starts off, they're like, yeah, I can do select from, and then you get to joins. It's like it requires some thought. So getting the hang of those is very important. The second thing is common table expressions that we've done today. The idea of breaking down complex queries into smaller steps, just as you do with like Python or any other programming language, that is very important. So if you take one thing away from today, then common table expressions is definitely a thing. Window functions are another tricky thing. We sometimes do code alongs on those. There's definitely courses on DataCamp on window functions. That's the sort of thing that just tend to come up in interviews because it's kind of gnarly syntax. It's one of those things really easy in Python or R, kind of tricky in SQL. And the fourth thing is writing user-defined functions. So if you can do those four things, you're going to breeze through any interviews.
Yeah, the subqueries I think are also really important because
yes.
I did a subquery in the select statement in this code along. I think they're more common in the where statement because it's often very useful to filter data by the result of another query. So that's useful.
Absolutely. All right. So another one here. So this comes from Kosal. So how can you see heteroscedasticity from eyeballing a graph? So I know you did an article on this recently, right? A tutorial.
Oh, right. Yeah, I did. I wrote something on the tutorial section for that. Heteroscedasticity. In that case, it was a funnel shape, and that's very common when you create a scatter plot. It looks a little bit like a V, and it could look like the opposite of it. It's where the variance becomes unequal. It's a little harder to spot heteroscedasticity if you have seasonal data with an up and down pattern, but you would look for wider variance at certain highs or lows. So I noted that, like, I couldn't help but say it, but it wasn't particularly relevant for this code along because, as you saw, we did an averaging, and it wasn't even that much heteroscedasticity anyway. But funnel shape, it's an issue if you want to make sure you talk about the confidence in your estimates. Because you're gonna be less confident about certain ranges of data if the spread is wider.
Absolutely. I think what's the plot you normally use? I think it's residuals versus fitted values in your model. I think that's the standard plot you use for looking at heteroscedasticity.
Yeah, that's a great one.
Wonderful. All right. So, there's a good one here from Gustavo. So Gustavo says, I work with price optimization using generalized additive models. I'm not a math expert. Is this similar to the derivatives used at the end of the notebook?
I'm not 100% certain, actually. That's a great question. The math expert part, it's really funny. No one feels like they're a math expert. I went to a pet store, and there was a guy who was selling an aquarium, and he was like, "Oh, this is how you figure out how many gallons are in the fish tank. You multiply the width by the height by the length, and then you divide by this magic number 231, and somehow that gets you the number of gallons in the fish tank." And that made me laugh because he was so close. It's like there were 231 cubic inches in a gallon. Like, I didn't know that, but I could tell that that's what he was saying when he said it. So some people like say, "Oh, I'm not math." Like, you can do the math, like we would work out the derivatives, and Mistral and all these LLMs help. But okay, back to the point. I think about these derivatives as being a little bit more like hyperparameter tuning also. So if you're especially interested in that part, we have courses about like gradient descent and you're finding a local maximum. And so you're finding the place at the top of the parabola, or at the bottom if it's a minimizing function where the derivative is going to equal 0 and change. And so that was really the way I thought about it. It's like in the relationship of machine learning, but this is a little bit more in pricing optimization. I did not really especially answer that question. So
all right. So yeah, the short answer is, if you're interested in optimization I would say don't do it in SQL in general. If it's going to be complicated, you want to use Python or R. We do have a fairly extensive series of courses on optimization in Python. I would say check out those. I think it's called Introduction to Optimization. Maybe Introduction to Optimization in Python. That's the first course you want to get through. There's a few of them. They use very extensively in things like supply chain analysis, as well as like other economic stuff like price optimization. Generalized additive models are also very cool. I can't remember whether we got a Python course. I remember making an R course on that many years ago, or being involved in that. So yeah, there are courses on that on DataCamp. Optimization is a huge field, and yeah, please do check out the courses. All right, with that, we are at time. So thank you once again, Joseph. Also say that we have got another webinar coming up tomorrow. It's called A Playbook for AI Governance. So if your organization is involved in like trying to, not do stupid stuff with AI, then please do check that out tomorrow. And then next week, on Tuesday, we've got a code along on using Google Analytics 4, so the latest version of Google Analytics, for understanding your customer journey. And then there's a session on Wednesday about does AI help or harm skill building? So if you're trying to work out how to learn, is AI going to help you, or is it going to just rot your brain and stop you thinking? So lots of great sessions. Please do come back for those. In the meantime, thank you to everyone who asked a question. Thank you to everyone who showed up today, and I hope to see you all again soon. All right, goodbye.